Hello everyone. In this video I'll walk you through my molecular dynamics simulation assignment for ES 658. So the first step is to select a protein from a curated list of 15 single domain single chain proteins. So this is the script of the Python script, and we begin by importing the necessary libraries, and then the script defines a function download.pdb. Then we download it. After running, then in the files we can see that there's the pdb file, downloaded pdb file, so we can download it. And then once we have downloaded the pdb file, here's my directory, working directory. So I've downloaded it here. So once we are done with the download, we need to prepare it for simulation using vmd. So we open terminal, and then we type vmd plus the protein name. And in the main panel, after loading of vmd, in the main panel we see that the total number of atoms in this pdb structure is 3009 and frames is 1. And by graphical representation we can see that if we select protein and then coloring method, if we keep secondary structure and new cartoon, so we can double click on the lines and we'll obtain the structure somewhat like this, which contains alpha helices and turns. So the frames is 1 here because we do not have any trajectory as of now. So now that the protein is generated over here, we can see it. Let us clean the pdb file. So we go to extension tk console. First we select a protein, set select atom, select top protein, then $cell write pdb into a new file, that is 6r2g.pdb. Now we have a new file named 6r2g.pdb. We will delete the existing file that was there. We will do mol delete all. We will again load the pdb structure that we have formed. So after loading, mol add file 62rg.pdb. So after loading we only have the coordinates in our pdb file, but we need other topological data like what are the bond angles present, the dihedral information. So to obtain that information, we generate another file of format psf. So in this file we'll have all those information regarding the protein. So in vmd we have a plugin known as automatic psf builder that is very user friendly. We do not have to run any type of backend code to generate the psf file. This psf builder creates the psf file in explore format. There are other formats, but we'll click to this. We'll go to modeling automatic psf builder, then check whether the molecule or the protein is loaded or not. Then the output will be the file name and underscore auto psf. We'll keep it as default. Then we load the input files, guess and split the chains, create chains, and then apply patches. So once we are done with all of these, we can see that our molecule has been successfully generated. So now we can see that two structures have been generated, and we will do mol delete all, and then again we will load the auto psf files that we have generated. Mol new 6r2g auto psf .psf, mol add file 6r2g auto psf .pdb. So for this we require all hydrogen atoms to be explicitly present. Now the solvation process is being performed. So the same way we browse, and then we give a box padding of 20 angstrom on all sides of the protein. Then the same way solvate.psf and solvate.pdb would be saved. In the solvate plugin we then solve it. So after solvation, on visualization, In the panel, we can see that that surrounding our protein there are several water molecules that have been added, creating a box padding. So after this visualization, see, we have created a cuboidal box, to be precise. So next, after this, if we check for the PBC get, like if we no, we first will delete all the files and then again add the solvate files. Mol new solvate dot 6r2 solvate dot psf mol add file solvate dot pdb. So our structure looks like this. So if we do pbc get now, we will get a certain coordinates to a system. So now we will check the charge. For that, we are creating two selections, one for protein and one for water, and we will check that what is the current charge of the system. So set cell 1, atom select top protein, set cell 2, atom select top waters. So now we will check the charge. So eval vec add atom select dollar cell 1 get charge. So now we can see that the current net charge of the protein is approximately minus 1.99. So we need to add positive ions to basically neutralize it. And we can also check for selection 2, that is waters, and we know that it will be 0. So now we need to neutralize the system. For doing that, what we will do is we'll go to extension modeling, add ions, PSF browse, and then we will ionize the system. So in there we'll get two files, ionize.psf and ionize.pdb. We will change it to 0.5, the neutralization of NaCl concentration, and then we will auto ionize it. Yes, once it is all done, we will delete all the existing files that are present, and now we will load mol new ionize.psf. Then we will write mol add file ionize.pdb. Ionized.pdb. So now again we will create a selection. So this is how it looks. So again we will create a selection. Say for all, we will do set cell 3, and now if we calculate the get charge for the net system, like atom select top all, then if we calculate the charge, eval vcad set dollar cell 3 get charge, what we see is it is to the power of minus 6. So it is very negligible charge. So in short, we have neutralized the system. So this step essentially maintains the overall charge balance. So now we are ready to simulate, like perform a molecular dynamics simulation. So we first look into our working directory, and then we open the minimize.conf file, because before running the actual molecular dynamics simulation, we perform energy minimization. So this process essentially removes steric clashes and optimizes the initial structure for stability. And there are the minimize.conf file contains essential simulation parameters. So all of this I have changed to my current directory. And one important aspect here is the periodic boundary condition. So for that we need to go to VMD again, TK console, then we do measure center cell $cell 3. So we will get the cell origin over here. So we'll copy and paste one by one the values. So before running, so here I will talk about, while I'm copy and pasting, I'll talk about the molecular dynamic simulation and energy minimization stage. So before running the actual molecular dynamic simulation, we perform energy simulation, energy minimization. So we run NAMD using a configuration file, and the parameter, like the file contains input structure files, ionize.pdb and PSF, the charm force field parameters, the number of minimization steps, which I'll be talking about in a while. So energy minimization step is an important part. The output of this would be a minimized structure that is free from any bad initial contacts, and we are getting it to a stable, like low energy state. So now we have, if we look into the PBC get, then we have gotten vectors, each of the vectors. So once that is gone, like once that is done, I will be minimizing it for 1000 steps, which I'll be showing you. So these are the vectors, cell basis vector. So once this is done, the minimization step is done, we will run the simulation. So in this, depending on your system, you can increase or decrease your time steps, but 1000 is what we have asked to do, so 1000 steps. Now we'll save and close the minimize.conf file, and then we'll write namd2, because we are running a simulation on namd. So we'll write namd2 minimize.conf greater than minimize.log. So now it will start running, and all the data, if we want to check that our NAMD simulation is running or not, it has stopped, it is completed. So I'll talk about it later. If we do nano.npt.conf, we open the npt configuration file for equilibration using npt ensemble. So after a minimization, we equilibrate the system under constant pressure and temperature. The NPT simulation maintains a realistic physiological environment. So this is the minimize output. So I have created two output files, so that I can save minimized output in a different file and NPT in a different file. So the input for NPT simulation would be the output of minimize, restart some outputs of minimize. So we are running it for 2000 time steps, and the rest all remain same. The parameters, we have to set our working path for the parameters. So yeah, I was in NPT simulation. So NPT simulation maintains a realistic physiological environment by controlling temperature and pressure. So here after npt.conf, we do namd2 npt.conf greater than npt.log. So we run 2000 time steps in this phase. So the output files would be npt.dcd and npt.restart, just like that. So now it is completed. We can see the npt.log file. It will show that it has run for 2000 time steps and it is completed. Program is finished. So now that we have all the output files, we try to check the trajectory in VMD. So we load the ionize.psf, and into that on VMD. Then into that we add our npd.dcd file that has been generated after the NPT simulation. So after that we load to visualize the point is, you can see how it looks. The point of doing this is to visually inspect the simulation to check for proper solvation, or whether there are structural distortions or not, or are there any atoms flying away. So here are some graphical representations. I'm changing it to enhance the representative view so that we can visualize it better. So it looks something like this. So this completes our setup and equilibration process, I could say. And the prepared system is now ready for further molecular dynamic simulations. I mean, such as if we want to do production runs or free energy calculations. So this is the protein without the solvation box, and we can see it's a huge protein. So after that, if we go again and deselect it, we can see the solvation, and with the side chains and the water molecules, how it looks. This is the overall view of NPT simulation that we have conducted. This workflow ensures that we start with a stable and properly equilibrated system, which is crucial for obtaining meaningful results in molecular simulations.